Dear students, today we will be discussing about fundamentals of solar concentrating collectors and analysis of parabolic trough collector. Now, what is concentrating solar power technology? This concentrating solar power technology utilizes focused sunlight. The concentrators increases the amount of incident energy on the observer surface as compared to that on the concentrator aperture. And this CSP technology utilizes mirrors or lenses to concentrate sun's energy and convert it into high temperature heat. So, the kind of collectors we are discussing in the last classes, those collectors could be employed for generation of fluid temperature of about 100 or slightly more than 100 degree C. But if we have to generate high temperature, or we have to think of application of high temperature application more than say 200, 300 or maybe 400. So, we need to go for concentrating solar collectors. Okay. So, how it will work, that is what we have explained here, and with the help of other slides we will understand what is the importance of this technology as far as high temperature application generation is concerned. So, this concentrating solar power technology follows sun so that the beam radiation are always focused on the observer. So, as you can see here, a solar concentrator generally consists of a reflector. This is a reflector, okay, or concentrator we can say, and this is a receiver. So, solar radiation comes and strike on this reflector and it reflects to this observer. Okay, that is how it works, and heat transfer fluid flow through this receiver, and then that can be collected in a collection unit, and that can be applied or used as per the applications. So, we need a focusing device. This is nothing but a focusing device, an observer or receiver. So, this is an observer or receiver. So, that may be with or without transparent cover sometimes. So, if we draw this tube through which heat transfer fluid flows, so this may be no steel or maybe copper. Okay. So, material of construction is copper, and just above it we will have a glass transparent cover. Okay. This is glass. So, this is glass. Okay. So, that is why it is said with or without transparent cover, and of course, we need a tracking device for continuously following the sun. Okay. So, in case of flat plate collector, that kind of systems are not required. So, that is installed in a location based on the phi value or latitude value, okay, and that is fixed throughout the year. And but in case of concentrating collector, we need to rotate the device based on the solar radiation or to capture solar radiation throughout the day. So, there are some advantages of this kind of technologies. So, first is it is a better thermodynamic efficiency because its operating temperature is higher or range of temperature is higher, and less material requirement compared to flat plate collector, and reduced storage cost. Okay. So, these are the primary advantages of these solar concentrating collectors, and as you can say, or as we have said, no temperature as high as 3500 degrees C have been achieved by using this kind of collectors. Okay. So, these are high temperature collectors. These solar collectors are used for thermal as well as PV conversion of solar energy. So, there are some drawbacks, like we cannot employ diffuse radiation for energy conversion. Okay. Only beam radiation are applied in case of CSP, and that is why we need a clear sky or cloudless sky for installation of this kind of devices. So, how this solar concentrator works? If we have to see, this concentrating solar power system generate electricity with heat, that we must know. This concentrating solar collectors use mirrors and lenses to concentrate and focus sunlight onto a thermal receiver similar to a boiler tube like conventional power plant. The receiver absorbs and converts sunlight into heat. Okay? The heat is then transported to steam generator or engine where it is converted to electricity, right. So, when we talk about solar PV system, so it converts sunlight to electricity directly, but in case of solar concentrating collectors, we are utilizing thermal energy to generate electricity. So, first we have to convert this solar energy to heat, then heat has to be converted to electricity by using this generator. Okay? So, CSP technology generate electricity for a variety of applications like ranging from remote power systems as small as few kilowatt up to grid connected applications of 200 to 350 megawatt or more. A concentrating solar power system that produces 350 megawatt of electricity displaces the energy equivalent of 2.3 million barrels of oil. Okay? So, which is very advantageous. And now, let us pay more attention on this thermomechanical system, how this heat energy is converted to electricity. So, as we say, thermomechanical system which convert solar thermal energy to mechanical energy through heat engine using Rankine cycle, maybe Stirling cycle, maybe Breton cycle. Okay? So, this mechanical energy produced may be used as soft power such as water lifting, okay? And this mechanical energy produced may also be converted to electricity using generator. So, what are the limitations of this conversion? This conversion efficiency is low, it is about 9 to 18%. The efficiency of the collector system decreases as the collection temperature increases, which is reverse in case of heat engine. The efficiency of the heat engine increases as the working fluid temperature increases. The solar collectors are generally more expensive than engine, and a part of thermal energy is lost during the transportation of the working fluid from the collector to the heat engine. That has to be considered. A very large area is required to install the solar collector system. Okay? And due to intermittent nature of solar energy, storage of thermal energy is also important. Okay? Now, let us see this picture, how this high temperature heat which is generated in the receiver system. Okay? So, as you can see, thermic fluids are used in the tube through which heat exchange takes place, solar radiation. So, maybe this is the collector. So, heat radiation falls here, beam radiation falls here and strikes in the receiver system. Okay? So, heat transfer fluid flows. So, here this heat will be very high. If we talk about the parabolic trough, maybe 350 to 400 degree C, it is a very high temperature. Okay? So, the thermic fluid will be heated up, okay, and then that will move to thermal generator or maybe heat exchanger. So, that heat will be utilized and then that heat will be used for heating the secondary fluid, okay, and then it will pass to the steam turbine, okay, because this once that fluid what is used in this Rankine cycle will be expanded in the turbine, okay, and that mechanical energy can be converted to electrical energy by using this generator, right. So, of course heat rejection will be there from the turbine. So this will work in a closed loop. Okay. So this heat transfer fluid, or say the fluid what is used in this cycle, may be different from the fluid what is used in this concentrator cycle, right. So this is how from thermal collectors to the electricity generation takes place. Now let us learn some of the parameters which characterizes solar concentrators, like aperture area. So if we talk about this tube and this is the reflector part, so this area is nothing but aperture area. Okay. The area through which solar radiation is incident is nothing but aperture area, and this observer area is something like that. Okay. This is a very long tube. If we talk about parabolic trough, the total area of the observer surface that receives the concentrated radiation, it is also the area from where useful energy can be obtained. Okay. And then acceptance angle, which is represented by 2 theta s, which defines the angular limit to which the incident ray may deviate from the normal to the aperture plane and still reach the observer or receiver. Okay. So this is the aperture angle what you can see here. So this is sun and this is the receiver, okay, earth surface, right. And also we need to know what is intercept factor, which defined as the ratio of energy intercepted by the observer of a given width to the total energy redirected by the focusing device. Okay. So the amount of radiation which is striking onto this observer. Okay. So some of the radiations may not be striking here. Okay. So it may goes off, or maybe it is coming in that way, and then it might not be striking this observer. So that is why this factor need to be considered. Of course, we are looking for unity, but always we will not get this unity. And also we need to know what is optical efficiency. So this optical efficiency defines the energy absorbed by the observer to the energy incident on the concentrator's aperture. It includes the effect of mirror or lens surface shape and reflection transmission losses, tracking accuracy, shading, receiver cover transmittance, absorptance of the observer, and solar beam incident or solar beam incidence effects. So let us define concentration ratio. Okay. So how we can define concentration ratio? Concentration ratio is the ratio of aperture area to the observer area. Okay. So as I am writing this again and again, so this is an aperture area. So maybe A I can write, and this is the observer area. Okay. So this AA by AP is nothing but C, which is concentration ratio, right. The local concentration ratio can also be defined, which is the ratio of solar radiation at any point on the observer surface to the incident radiation at the aperture of the solar concentrator. Okay. So you can see the definition of C here, and this is very important point. Like a concentrator with large acceptance angle needs only seasonal adjustment, while a concentrator with small acceptance angle is required to track the sun continuously. Okay. So this is very, very important. So sometimes we need to design the concentrator in such a way that it has to operate continuously, and sometimes intermittent adjustment is also fine. Okay. So this defines acceptance angle is important for deciding this adjustment. Now let us see the radiative actions between the sun and the receiver. So if we consider a black body, sun is always considered as a black body having temperature Ts, and the radiation from the sun on the aperture or receiver is the fraction of the radiation emitted by the sun which is intercepted by the aperture, which can be represented by this expression Qs to R is equal to AA R square by capital R square sigma Ts to the power of 4. Okay? So, sigma is known to us, which is Stephens-Boltzmann's constant, and a perfect receiver such as black body radiates energy equal to AR TR to the power 4, this is the receiver temperature, and a function of this reaches the sun, and a fraction of this reaches the sun. So, this can be expressed by using this expression, right. Now, if I am interested for estimation of maximum concentration ratio, then we need to do something. Okay? Like when TR and TS are the same or fixed values of this TR and TS, the second law of thermodynamics requires that heat transfer from source to the receiver or sun to the receiver should be equal to receiver to the sun. So, if we use this expression, then what we will get? This kind of expression. Okay? Now, since the maximum value of ER to S is unity, the maximum concentration ratio for circular concentrator is found to be 1 by sin square theta S. Okay? This is for circular concentrator. So, geometry of the concentrator may be different. So, this is for circular concentrator, and for linear concentrators the maximum concentration ratio is found to be 1 by sin of theta S, right. So, if we know this theta S, which is equal to 0.257 degree, the maximum possible concentration ratio for circular concentrator is calculated to be about 46,000, and for linear concentrator it is found to be about 215. Okay? Now, let us pay attention about the different configurations of concentrating collectors. As you can see, these are tubes and one reflector is placed at the bottom of the tubes, and this is one more configurations, which is nothing but tubular absorber with specular cups reflectors. So, this kind of configurations are there to increase the concentration ratio. So, normally what happen in case of flat plate collector, we will have concentration ratio is equal to 1. Okay? So, if we can increase the concentration ratio, so we can increase the operating temperature of the collector, right. So, these are different attempts, and this is a compound configuration. So, where we can have more radiation exposure and then we can get slightly higher concentration ratio. Okay? And this configuration is for say parabolic trough. So, receiver is here, this is the reflector. Okay? So, these rays are focused on this axis because this is a long tube, not a point. Okay? And this configuration is for Fresnel reflectors, and this configuration is for arrays of heliostats with central receiver system. Okay? So, we will learn details with time. So, as you understand, for point focus system, this concentration ratio can be defined as 1 by sin square theta, and for line focus system this is 1 by sin theta. Okay? So, if we know this theta value, then we can straightway calculate what will be the maximum concentration ratio for a point focus system and for a line focus system, right. And as I said, so these are the attempts to increase the concentration ratios, though these first three, the maximum concentration ratio can be achieved is 4. Okay? And then other configurations, of course, no concentration ratios are quite high. The actual value of this concentration ratio C is much lower, since the acceptance angle is usually greater than 0.267 degree. This includes tracking errors, imperfections in the reflecting or refracting components of the concentrator, mechanical misalignments, etc. Okay? So, these are the causes of reduction of this actual concentration ratio. And this slide shows the collector type based on concentration ratio. Okay? So, as you can see, this planar and non-concentrating type, which provides concentration ratios of up to 4 and are of flat plate type. Okay. So, if you see this figure, this vertical axis shows concentration ratio and horizontal axis shows receiver temperature. Okay. So, these are the lower limits and this is the band. Okay. Normally, this is the band at which the concentration ratio falls when temperature increases. Okay. And ranges of operation or ranges of concentration ratios are shown. So, this is for paraboloid. Okay. You can see the range of operation. Of course, that can be adjusted by using different means, and for conical configurations you can see this is the range, and for cylindrical this is the range. Okay. So, for line focus system we can have concentration ratio up to 10, and for point focus system it is very high. Okay. So, this slide shows about the comparison of flat plate collector and concentrating collector. As already you are aware that these flat plate collectors are normally used for low temperature applications. So, maximum may be 100-110 degrees C. Okay. For this kind of configurations for concentrator, it may go up to 3500 degrees C, okay, starting from 260 degree C, right. And here in case of flat plate collectors, what primary advantage is, we can employ both normal and diffuse radiation, but in case of concentrator only normal radiations are applied for energy conversion. So, diffuse radiation cannot be employed, or even though diffuse radiation falls on these devices, but contribution of these radiations are very less. And here no tracking is required, but in case of concentrating collectors tracking is must, and because of this mechanically it is unstable and then it requires maintenance, but in case of flat plate collector maintenance is very less. So, let us classify the concentrating collectors. There are different modes of classification. So, based on the aperture type, it is a reflecting type utilizing Fresnel lens, or refracting type utilizing mirrors. So, if we have to use mirrors, then reflecting surface may be parabolic, spherical or flat, that may be continuous or segmented. And classification based on image formation may be non-imaging system or non-imaging type, or may be imaging type. So, under imaging type again we have two classes like line focusing type or point focusing type. And based on operating temperatures may be low temperature, medium temperature and high temperature. And then fourth category of classification is based on tracking system. So, single tracking system or 2 axis or double tracking system. Okay. Sometimes we need double tracking system to track the sun in order to capture more beam radiation. Now, let us see different CSP technologies, what is available. So, first technology is parabolic trough, then this Stirling central power receiver system, then Fresnel collector. Okay. So, what you can see here, so this is a concentrator, okay. This part is concentrator and this is receiver system. So, solar radiation falls here and is reflected to this focal axis. Okay. So, reflector, then observer tube, then this is solar field piping. So, here as you can see, this is an observer tube, then over it is a glass cover. So, this is maintained vacuum. So, this is vacuum, okay, in order to reduce the heat losses, right. So, in case of this Stirling system, so reflector is something like this and it will focus on this system. Okay. So, engine is placed, normally Stirling engines are attached here, it is a external combustion engine. So, heat is supplied here and then expansion of fluid will be there, and from that electricity can be generated directly. And this is central power receiver system. So, here lot of heliostats are there. So, these are heliostats, okay, mirrors. Solar radiation falls and it is reflected to this receiver system. Okay. So, normally molten salt and oils are used. Okay. So, that may be collected and later on we will have powerhouse here. So, this heat exchange will be there to the secondary fluid of this Rankine cycle, and then from that if we have generator we can generate electricity. Okay. This is solar tower, and Fresnel collectors are something like these are segmented pieces of mirrors. Solar radiation falls here and strike on this absorber tube, and then heated fluid can be taken out for applications. And we can compare those technologies with different aspects, like for parabolic trough collectors, whether possibility of storage systems are there or not, okay, or what are the other advantages, we can list it out. Okay. So, if we talk about possibility of integration of storage system, it is yes, it is possible, and advantages includes relatively low installation cost and large experimental feedback is there in case of parabolic trough collector, and disadvantages are relatively large area occupied, low thermodynamic efficiency due to low temperature. Okay. So, since this temperature difference is low, because of that we will have lower thermodynamic efficiency. And in case of linear Fresnel reflectors, storage is possible, and advantage is relatively low installation cost, and disadvantages include low thermodynamic efficiency due to low operating temperature, which is primary. For solar power tower, it is highly desirable that kind of storage system, because that has to be stored, huge amount of heat is generated and that has to be stored for night use or maybe when demand is very, very high, and its thermodynamic efficiency is high as the operating temperatures are high, but it requires large space area and relatively high installation cost, and high heat losses are taking place for this kind of technologies. And in case of parabolic dish, it is difficult to install storage system. Advantages are relatively small area occupied and high thermodynamic efficiency, but disadvantages are relatively high installation cost and little experimental feedback. Okay. So, this slide shows about the comparison of 4 different CSP technologies. Now, let us pay attention about thermal analysis of concentrating collectors. So, under steady state condition, the energy balance on the observer plate can be written as something like this. Okay. So, this QE is the useful heat gain and AA is the effective area of the aperture of the concentrator, and S is the solar beam radiation per unit effective aperture area absorbed in the absorber, and QL is the rate of heat loss from the absorber. Okay. So, if we write QL, that is rate of heat loss in terms of overall loss coefficient, so we can use this expression. Okay. So, QL is UL AP TPM minus TA. So, TPM is average temperature of the absorber surface, okay, and UL is overall loss coefficient. Okay. So, if we use it here, QU is AP into S minus UL, then AP TPPM minus TA, okay, and if we, so this is A, okay. So, if we take out A S minus UL AP by AA TPM minus TA. Okay. So, we can define concentration ratio now. Already we know what is concentration ratio. aperture area to the absorber area, right. So, this will be 1 by C, right. So, QE will be A S minus UL by C TPM minus TA. Okay. So, this is L, right. So, this will be useful heat gain, right. So, that is how we can write this expression AP multiplied by S minus UL by C TPM minus TA, right, and C is the concentration ratio. And this slide shows the efficiency versus receiver temperature. Okay. So, this is the system efficiency and this is the receiver temperature, okay, at different concentration ratios. Okay. So, these are different concentration ratios. So, it goes maximum and then it come back to 0. Okay. So, it shows the variation of efficiency with respect to receiver temperature at different concentration ratios. So, for flat plate collector concentration ratio is 1, for parabolic trough it is about 80, for solar tower it is 500, parabolic dish about 2000. Okay. So, this overall efficiency of a CSP plant can be expressed something like this: eta system is eta collector multiplied by eta Carnot. Okay. So, if you know the Carnot efficiency and collector efficiency, then straight away you can calculate what will be the system efficiency of the plant. So, with increase in temperature, this collector efficiency decreases, but Carnot efficiency is increases, right. So, that is how we can get higher system efficiency if Carnot efficiency is significantly higher. And this slide shows the applications of CSP in commercial scale and domestic level. So, for commercial scale, the CSP can be applied for power generation in standalone mode, or maybe grid connected system, or maybe hybrid system, or maybe to meet the demand of thermal requirement, hot water and steam generation, air conditioning, absorption chillers, desalination of seawater by evaporation, solar chemistry, manufacture of metals and semiconductors, hydrogen production, maybe water splitting, or material testing under extreme conditions like design of materials for shuttle reentry. Okay. Or as far as domestic applications are concerned, it may be applied for hot water generation, or maybe HVAC or air conditioning system, and solar steam cooking, solar oven or cookers, then solar food drying. And also we can compare these technologies with different parameters. Okay. So, like relative cost, then land occupancy, thermodynamic efficiency, operating temperature, solar concentration ratio, and then improvement potential, right. So, as far as parabolic trough is concerned, it is a relatively low cost, but large land is required. Okay. But thermodynamic efficiency is lower, and operating temperature ranges from 20 to 400 degrees C, and concentration ratio varies from 15 to 45, and improvement potential is limited. Okay. So, for solar power technology or solar power tower, so it is a very high cost, and occupancy is medium. So, not much land area is required. Thermodynamic efficiency is higher, and operating temperature is also higher. Okay. At concentration ratio, you can see it varies from 150 to 1500. Okay. And improvement potential is very significant. In case of linear Fresnel reflector, it is a relatively low cost, and land occupancy is medium, thermodynamic efficiency is low, operating temperature may go up to 300 degrees C, and concentration ratio varies from 10 to 40, and there are a lot of scope for improvement. And parabolic disc collector, so it is a very high cost, land requirement is small, thermodynamic efficiency is high because operating temperatures are high, and you can see the operating temperature 120 to 1500 degrees C, and concentration ratio varies up to 1000, and it has got a lot of potential for improvement. So now let us pay attention about the analysis of parabolic trough collector. Okay. So let us consider this configuration. So we will have solar field, then you have observer tube, and then reflector, right. So if we take a section, so it appears like this. So this is concentrator, okay, and this is the receiver system. So when we call receiver system, it includes observer tube plus this glass cover, okay, which is placed concentrically, and vacuum is maintained in between these, okay. So if we consider a section, so this is the tube through which heat transfer fluid flows, okay, and if we take the length of the tube, okay, this is the length of the tube, and start from is x is equal to 0, maybe x is equal to 0 here, okay, and it moves something like this, and take a section dx, okay. So fluid is flowing from this tube, so maybe at this point fluid temperature is Tf, and at this point this fluid temperature is Tf plus dTf, okay. So we will assume some parameters or some of the information like radiation flux is same along the length, okay. So it is assumed that this radiation flux which is falling in the observer is same, okay. Of course there will be some differences in actual case, but what we will consider is same, and temperature drop across the observer tube and the glass cover are neglected, okay. So this is observer tube, this is a glass cover, so temperature drop is neglected, okay, it will be same, right. So this aperture of the concentrator is W, which is represented here, and length is L, is the length of the tube is L. So this length, or you can say this is the length, okay. So this length is L, so I can write this way also, this length will be L, okay, along the length. So length of this tube, and rim angle is phi r, it should be here. So rim angle is phi r, so this is the phi r, okay. And this observer inner diameter is di and outer diameter is do, okay, and concentric glass cover inner diameter is dci. So here, so thickness will be here, so it has got some thickness, and outer diameter is dco, right. And the fluid is heated from inlet temperature Tfi here, at this point is Tfi, it is Tfo, okay. So outlet temperature is Tfo, okay, and let m be the mass flow rate, okay, mass flow rate of the fluid that is flowing through the tube, right. And if we are interested about concentration ratio of this configuration, so it will be something like this: effective aperture area to the observer tube area, okay. So this effective aperture area is something like W minus this d, okay, d naught is the outer diameter of the tube, multiplied by L, okay, is the length, to the pi dl. So d naught is the diameter of this tube, okay. So that way, if this L is common in numerator and denominator, this will goes off, then W minus d naught divided by pi d naught is the expression for concentration ratio. So if we know aperture of the concentrator and then outer diameter of the observer, then we can straightway calculate what will be the concentration ratio of that configuration, okay. Now let us draw an energy balance or write an energy balance expression on the observer plate. So this energy balance on an elementary slice of the observer tube at a distance x from the inlet. So this gives a relationship of something like this. So QU is the useful heat gain, which is equal to IB into RB W minus D naught rho gamma tau alpha is for beam radiation, okay, because beam radiation is only employed. So this part is the direct radiation which is falling on the observer tube, and this part is for losses. So, this component is coming from the reflector. So, from here, from this reflector, solar radiation is falling here, it will go, this will go. Okay. So, first component is contribution from this reflected radiations. Okay. Second component is, since this is exposed to the sun, so it will directly fall on this absorber. Okay. And this is the losses. So, UL it take care of this conduction and convection losses, okay, from the absorber tube, right. So, this IB is the beam radiation, and tilt, this RB is the that component which has to be multiplied, because all the radiations are not coming. So, some losses will be there. Okay. Then this is the reflectivity of the reflector, and this is the gamma which has to be multiplied, because all the radiations are not coming and striking on the absorber, and these values are already defined, and these are the losses, and Tp is the absorber plate temperature or absorber tube temperature, this is the ambient temperature, and this is the dx, what is the slice. Okay. So, absorber solar flux we can write something like this. Okay. So, using this equation in equation A, then this equation simplifies to something like this. Okay. And also heat gain rate, we know HF multiplied by pi di Tp minus Tfi dx, which is nothing but mCp dt, because mass is flowing. So, m is the mass product under specific heat of the thermic fluid, and we know the temperature difference Tfi and Tfo. Okay. From that we can calculate what is the rate of heat transfer, is mCp dt, right. So, now combining this equation C and D, what we will have useful heat gain in that particular section will be something like this. So, F dash is the collector efficiency factor, which can be expressed something like this. Okay. And if we combine this equation E and F, then we will have this kind of equation, and we need to integrate this using the initial conditions at x is equal to 0, Tf is equal to Tfi, which is already shown, right. So, once you do it, then we will get a temperature distribution of something like this. Okay. So, fluid temperature is obtained by putting Tf is equal to Tfi and x is equal to x naught. So, now this should be Tfo. So, if x is equal to L, the Tf will be Tfo, right. So, if we substitute this, then we can have this kind of configuration. So, now we can calculate what is the useful heat gain rate. Okay. So, this useful heat gain rate can be calculated, and it is found to be something like this, right. And also we can define collector heat removal factor, which is expressed by this expression. Okay. So, once we know this, then we can calculate what will be the instantaneous efficiency of the collector. So, this instantaneous efficiency is expressed something like QU by IB into RB plus ID into RD W into L. Okay. So, this is the diffuse radiation component which is coming from the ground. Okay. Sometimes this may be neglected. Okay. If we neglect this term, then this equation for instantaneous collector efficiency simplifies to this equation. So, if we know QU and IB into RB multiplied by W into L, then straight away you can calculate what will be the instantaneous collector efficiency, right. So, RB already we know for beam radiation what is the RB, which is the cos theta by cos of theta z. Okay. So, there is a long expression for all the angles. So, this can be calculated, and IB is known, and see here no diffuse components are present. Okay. Only beam radiations are included. Okay. So, this analysis will be very much important to characterize a parabolic trough. So, we must know the procedure how this can be characterized. So, now next phase is how to calculate the heat transfer coefficient. So, once we know those values, instantaneous efficiency value, FR value, F dash values, and then useful heat gain, then we need to know the heat transfer coefficient, how this heat exchange is taking place from the collector to the absorber, then absorber tube to the glass tubes, and then fluid. So, all the things we need to calculate. Okay. So, this overall heat transfer coefficient and heat transfer correlations need to be understand. So, this is the QL, okay, heat losses. We can express QL in terms of UL as well, and also we can use this expression for calculation of heat loss. And then heat transfer coefficient between the absorber tube and the cover can be estimated by using this expression. This RA is the modified Reynolds number, okay, which is defined something like this. Okay. Once you know this, then finally what we can calculate the heat transfer coefficient from the plate to the cover. Okay. And then next phase is to calculate heat transfer coefficient on the outside surface of the cover. Okay. So, the correlations proposed by Hill parts are normally used. So, it is expressed Nusselt number is equal to C1 multiplied by Reynolds number to the power of n. Okay. So, there are different conditions for Reynolds number value between 40 to 4000, this C1 to be used as 0.615 and n will be 0.466, and for a value of Reynolds number between 4000 to 40,000, C1 to be used as 0.174 and n is equal to 0.618, and for this, so if Reynolds number is very high, which is more than 40,000 and less than 4 lakhs, then we need to use this set of data for calculation of heat transfer coefficient on the outside surface of the cover. Also, we can use some alternate correlations developed by Surcili and Bernstein. Okay. So, this correlation is valid up to a Reynolds number of 10 to the power of 7, and if this Reynolds number is in between 20,000 to 4 lakh, then we can go for this correlation. So, there is slight change in this value. Okay. So, this is the difference. So, here it will be 1 by 2 of this section, and but here it is 5 by 8 and then 4 by 5 whole to the power this bracket section. So, once you know this Reynolds number and Prandtl number is known at that temperature, and then we can calculate what is heat transfer coefficient, because Nusselt number is H, L or D. Now, it will be L H D by K, or sometimes it is D also. Okay. So, HL or HD by K. So, once we know this K, L or D, then we can calculate what is H, okay, or heat transfer coefficient. So, this heat transfer coefficient on the inside surface of the absorber tube, if I am interested to know, then we need to go for this kind of correlation. Okay. Nusselt number is equal to 3.66, okay, for the flow having Reynolds number less than 2000. Okay. So, if the flow is turbulent having Reynolds number more than 2000, then we need to use the correlations developed by Detach Voltaire, which is something like this. Nusselt number is equal to 0.023 multiplied by Reynolds number to the power of 0.8 and Prandtl number to the power of 0.4. Okay. So, we can calculate the heat transfer coefficient on the inside surface of the absorber tube by using these correlations. Okay. But while using this correlation, we must pay attention about this assumption, right. Just flow is fully developed, that assumption has to be done, and it is valid as L by Di is larger than 20. Okay. So, under that condition we can use no flow is fully developed, and we can have this kind of expression. And Hong and Barglis developed a correlation which is expressed something like this. Okay. So, apart from Reynolds number and Prandtl number, one term is there which is x. This x is nothing but tap twist ratio. Okay. So sometimes what happens, heat transfer in a flow can be augmented by using some kind of twisted taps. Okay. So if this kind of taps are introduced in that flow tube, then heat transfer coefficient enhances. Okay. So in order to define this twisted tap or this kind of configuration, we need to define this twist ratio. Okay. So this x is nothing but h by di. So h is nothing but length over which the tap is twisted through 180 degree. Okay. So this is something like twisting. Okay. So once it is twisted and it is introduced in that flow tube, okay, then it is investigated that heat transfer is augmented, okay, or heat transfer can be enhanced by applying twisted tap in a flow process. Okay. Also, once we done with this heat transfer coefficient, researchers are interested to know the pressure drop, how much pressure drop is taking place. Okay. So there are many correlations to investigate this pressure drop. One of the correlations which is applied here in concentrating collectors are proposed by Date and Singham, which is expressed something like this: F multiplied by Reynolds number is equal to 38.4 Reynolds number divided by x to the power of 0.05. Okay. So this value should be in between this range, and also this friction factor multiplied by Reynolds number can be expressed something like this. Okay. If this value is more than 100. Okay. So this C can be calculated by using this expression. Okay. So x is known to us from here, and then if we apply here, and we will get C2. Once we know C2 and Reynolds number is known to us, then we can calculate F, okay, which is friction factor. So once we know friction factor, we can calculate the pressure drop. Okay. So this is 4F L V square by twice G. Okay. So that way we can calculate the pressure drop, right. So let us summarize what we have discussed today. Primarily we have discussed the fundamentals of concentrating collectors and also the classifications which are made based on reflecting type utilizing mirrors, refracting type utilizing Fresnel lenses, imaging technologies. It may be point focus system or maybe line focus system. Okay. So if we are talking about point focus system, it's a high concentration ratio and its operating temperature is very high, and in case of line focus system, even though concentration ratio is comparatively higher, but it cannot achieve as normally done in case of point focus system. Okay. And there is also one basis of classifying is concentration ratio, which is nothing but the operating temperatures, as you can see. So as the operating temperature increases, this concentration ratio also increases. And tracking also one of the classifications. What kind of tracking normally adopted? Maybe single axis tracking, maybe double axis tracking. Okay. So based on the requirement, that can be decided. And also we have learned the energy balance on an observer plate of a concentrating collectors. So this QU can be expressed something like AP multiplied by S minus UL by C multiplied by TPM minus TA, where UL is the overall loss coefficient and AA is the aperture area, C is the concentration ratio. Okay. So if we know mean observer plate temperature or tube temperature and ambient and solar flux, we can calculate what will be the useful heat gain. Okay. Also we have learned the analysis of parabolic trough collectors and heat transfer coefficient. Okay. How this can be calculated, heat transfer coefficient can be calculated, and how this can be applied for calculation of useful heat gain, right. Because as you know, QU is S into AA minus QL. Okay. So this, in order to calculate this QL, we need to learn this heat transfer coefficient. So once we know this heat transfer coefficient of different system from where to where the heat transfer is taking place, so once you know this, we can substitute in this equation and we can calculate what will be the useful heat gain. Okay. So, I hope you have enjoyed this video. Thank you very much for watching.